Today we will talk about relativistic dynamics. How will the new revolution change our interpretation of physical concepts? Now, the dynamical quantities that depend on motion, such as kinetic energy and momentum, they depend on length, time, and velocities. When these are different, previously we have seen the cases of length contraction, time dilation, and relativistic velocity addition. How the velocity is measured in one frame of reference is related to the velocities measured in other frame of reference, that is moving with a constant velocity with respect to the previous frame. In order to understand how the kinetic energy and momentum change, let us first see an example of collision, elastic collision. Let's say in a reference frame O prime, you have two objects. One which is of weight mass 2m, and there is a second mass. The second object of mass m is, let's say, moving with some initial velocity of minus 0.75 c towards 2m. Now, using classical mechanics, you can calculate their final velocities. So v 2f, v prime 2f will be minus 0.5 c. I'm using here v prime symbol because it is measured in reference frame O prime. According to O prime, initial momentum pi prime can be found using this formula, and once we substitute all the values, we get the value of the initial momentum. Similarly, we can find final momentum, and after substituting values, we get the value of final momentum as minus 0.75 mc. So we can clearly see that the initial momentum is equal to the final momentum according to O prime. That confirms that momentum is conserved. However, if we now consider this frame of reference O prime moving with constant velocity of plus 0.55 c in x direction relative to another frame of reference O, then how would an observer in frame of reference O analyze this collision? Using this equation, we can actually now calculate the initial velocities of both these masses and final velocities of both these masses as observed by an observer in frame of reference O. So here are the velocity calculations for initial and final velocities of the two masses as according to observer in frame of reference O. So we can similarly calculate initial and final momentum according to observer O. We can see that according to observer in O, initial momentum is not equal to the final momentum. That means momentum is not conserved according to O. This collision experiment has shown that law of conservation of linear momentum, with momentum defined as P equals to mv, does not satisfy Einstein's first postulate. Therefore, we must find a new definition of P vector. Whatever we find the new formula for linear momentum, that formula must satisfy first the conservation of linear momentum, and then it should convert to the classical case at low speeds. Formula for relativistic momentum is given here. In this formula, note that the denominator has v and not u. V is the speed of an object. U typically we have denoted as the speed of frame of reference. Let's look at an example where 1 kg lump of metal is observed traveling with speed 0.4 c. Now you have to find its linear momentum and also calculate what would be the momentum if you double the speed. And let's compare the corresponding classical value of linear momentum. Using the formula given before, we can find the relativistic linear momentum to be 1.31 into 10 to the power 8 kg meter per second. Now if you double the speed, where V by C ratio is now 0.8, notice that linear momentum does not simply double. But if you calculate using the same formula, you will get the linear momentum. Notice this is more than 3 times the previous value. So linear momentum is not directly proportional to V as in classical case, but relativistic linear momentum has a different formula given here, which does not has a linear relationship with velocity v. Now if I want to plot how the linear momentum varies with velocity, I can do that for classical case and also for relativistic case. So here blue line represents how the classical value of linear momentum will vary with velocity. And this is here red curve representing how the relativistic momentum will vary with velocity. Notice here how the relativistic momentum is varying with velocity, and here the velocities are approaching the speed of light, but they're not higher than that, whereas classical mechanics does not impose any such a restriction on velocities. Now if you want to get the value of force, classically we use the formula F equals to ma to get the value of force if we know acceleration. But relativistically, the force acting on a body cannot be defined as ma, but it is defined as F equals to dp by dt. Now, having found a suitable relativistic definition for linear momentum p, our next task is to find energy of a body. Now there are again some requirements. As seen previously, here also for low speeds, this relativistic energy should reproduce as closely as possible to the classical definition of energy, of kinetic energy. And also the total energy of an isolated system of bodies should be conserved in all inertial frames. Now the definition that fits these requirements turns out to be, notice here that v is the velocity of particle or object or a body. Kinetic energy. Now this equation applies to any single body. For example, an elementary particle such as electron. It can be applied to assembly of particles like an atom. It can also be applied to assembly of atoms like a baseball, a rocket, or a star, or a car, and so on. Now let's look at what happens to this formula when velocity of a particle is much smaller than the speed of light. Now the 1 over square root of 1 minus v square by c square written as this, and we can again use the binomial approximation to get this value. Therefore, the value of energy can be approximately equal to this, which is further equal to mc square plus half mv square. We know that in classical case, the kinetic energy is given by half mv square. Here we have this extra term here. It's a special case when the velocity of a particle or an object is much smaller than the velocity of light. So we see that for a slow moving body, relativistic energy is equal to a constant term mc square plus a classical kinetic energy. Now this constant term mc square is independent of v, that is independent of velocity v, and a second term half mv square, that is precisely the classical kinetic energy of a body of mass m and speed v. In classical physics, it was believed that mass was always conserved, and the term mc square in the above equation would therefore have been an immutable constant. Further, you will recall that one was always at liberty to add or subtract an overall constant from the energy, since the zero of energy was arbitrary. Thus, in the classical context, this above equation implies that when velocity is much smaller than c, the relativistic energy E of a body is just the classical kinetic energy plus an irrelevant constant mc square. Therefore, the relativistic definition meets both our requirements, and our identification of this equation as the appropriate generalization of the classical notion of energy is complete. We'll also find that in relativity, the irrelevant constant mc square in this above equation is actually extremely important. The reason is that the classical law of conservation of mass turns out to be wrong. This law of conservation of mass was based mainly on 19th century measurements of masses in chemical reactions where no change of mass was ever detected. However, in the 20th century, nuclear processes were discovered in which large changes of mass occur, and even when the rest mass of certain particles disappears entirely, in the 20th century, however, nuclear processes were discovered in which large changes of mass occur, and even when where the rest mass of certain particles disappears entirely. Now it is clear from relativistic equation or non-relativistic equation that even when a body is at rest, that velocity is zero, its energy is not zero, but it is given by E equals to mc square, and that is the rest energy of mass m. And this energy exists even if an object of mass m is not moving. So this is the rest energy. If an object at rest has some energy, so what is the rest energy of a 1 kg metal? We can calculate that using formula E0 equals to mc square, and when we substitute, we get 9 into 10 to the power 16 joule, which is about the energy generated by a large power plant in 1 year, which is a lot of amount of energy. Now this incredible amount of energy would be of no interest if it could not be converted into other forms of energy. If that metal is uranium-235, about 1 part in 1000 of the rest energy can be converted into heat by the process of nuclear fission. Therefore, 1 kg of uranium-235 can yield fantastic 9 into 10 power 13 joule of heat. So what we have seen so far, that even when a body is at rest, its energy is not zero, but is given by the famous equation E equals to mc square, which is called the rest energy of mass m. And it can be converted into other forms such as kinetic energy of other bodies, and we'll see that in case in future. Now when the body is not at rest, we can think of this total energy given by this equation as equal to mc square plus some kinetic energy, and we know that this mc square is the rest energy and this k is kinetic energy. Therefore, kinetic energy K can be written as total energy minus this mc square. And this is the equation for our relativistic kinetic energy. As we have seen for other equations or other variables, here also, even for this relativistic kinetic energy, at slow speeds, this should convert back into classical kinetic energy of half mv square. So let's see what happens. At slow speeds, that is when v is much smaller than c, then 1 plus, again we can use this approximation to get this value. Now if I substitute back this value in total energy equation or in kinetic energy equation, k equals to E minus mc square, we get that at low speeds kinetic energy is approximately equal to half mv square, which is classical kinetic energy. So for special cases, at low speeds, it does convert back to classical kinetic energy. But in general, relativistic kinetic energy is different from half mv square, and it is given by this equation k equals to E minus mc square, where E is the total relativistic energy of an object. It can be written as this. Again, it looks different from classical kinetic energy of half mv square. For this relativistic kinetic energy, it implies that as v approaches c, this kinetic energy can approach infinity. So we can increase the kinetic energy of a particle without limit, and its speed will not exceed c. However, in classical case, when k is equal to half mv square, it implied that if we allow kinetic energy to increase without limit, v will also increase without limit, violating the second postulate. That is why the new relativistic kinetic energy is the correct form of energy. And again, revising that the relativistic total energy is given by E equals to k plus E naught, where E naught is the rest energy. Note that since this quantity is always greater than or equal to 1, the relativistic kinetic energy is always positive, just like its non-relativistic counterpart half mv square. So just revising a little bit, we found a new relativistic linear momentum equation, and we also know that this relativistic linear momentum is conserved. Second thing, we found a equation for total relativistic energy or relativistic total energy given by equation E equals to k plus E naught. So this relativistic total energy is conserved. So we can no longer use the equation of conservation of kinetic energy. We have to use relativistic linear momentum conservation equation or relativistic total energy conservation equation. In classical mechanics, a surprising number of interesting problems can be solved using just the law of energy and momentum conservation. However, In relativistic case, many such problems can also be solved, but now we will take total energy conservation and linear momentum conservation. And also, now mass is also not conserved in case of relativistic. We have seen that mass can also be converted into energy. Now we will look at the relation between relativistic momentum and total energy. So these are the two independent relations. If I take the square of both of these variables, I can get a relation, and then calculating p square c square, I can get a relation. I can calculate p square c square minus e square as, and after a little bit of mathematical calculation, you get that this value is equal to minus m square c to the power 4. So this brings us to an equation that is written as e square is equal to p square c square plus m square c to the power 4. And mc square here is nothing but our rest energy. So the second quantity, m square c square to the power 4, can also be written as e naught square. So this is our important relation between the momentum and total energy. Now this equation can also be written as E equals to square root of PC square plus square of MC square. In special case, when velocities of a body or a particle reaches speed of light or approaches speed of light, which is the case of high energy accelerators, in that case kinetic energy will be much greater than their rest mass energy or rest energy. In that case, total energy E can be written as approximately equal to Pc, which is an extreme relativistic approximation. Now I want to go back to the same equation again, which can be rewritten in this format. So it is clear that E square minus P square C square is invariant under Lorentz transformation, since mass and C are both constant. Again, for a special case when the speed of particle is much smaller than c, then the total energy reduces to p square over 2m. And also for a special case when particle is massless, that means when m equals to 0, that time E will be equal simply Pc. And that shows that the all massless particles, for example like photon, travel at the speed of light. Now before I go further, let's look at this equation again and how this relation can be understood. These three quantities E, Pc and Mc square are related like the sides of right triangle. In this right triangle, I can denote it like this in a triangle. When Pc is larger than Mc square, the energy is mostly kinetic. And it can be represented again using a right triangle. Now let's look at a question. Given that an electron has mass m equals to 9.109 into 10 power minus 31 kg, what is its rest energy in electron volt and what is its mass in electron volt per c square? So we will look at the two units that you have not seen before. If I just used the equation for rest mass energy or rest energy, I can simply get it as 81.87 into 10 power minus 15 joule. And how can be converted into electron volt? Using this conversion, we get this many electron volt, or I can write it as 0.511 mega electron volt. Now dividing both sides by c square, we get the value of mass in mega electron volt per c square. Previously, I had told you that the rest mass m is a form of energy, mc square, and that mass can be converted into another form of energy. So how can this mass be converted into energy? Now such conversions would require the classical law of conservation of mass to be violated. Now if the relativistic mechanics we have developed is correct, the non-conservation of mass is logically necessary and mass is not conserved. So, in relativistic mechanics, first, relativistic linear momentum is conserved, second, total energy is conserved, but mass is not conserved. Now let's consider two bodies that can come together to form a single composite body. Two bodies could be two atoms that can bind together to form a molecule, or two atomic nuclei that can fuse to form a larger nucleus. Because it is probably easier to think about everyday objects, we will imagine two macroscopic blocks. When the bodies are far apart, we take for granted that the forces between them are negligible. But when they are close together, there will be forces, and let's say those forces are repulsive in nature. And to hold the blocks together, we attach a pivoted catch to the second block, as shown in figure. Suppose now we push these two blocks together until the catch closes, as shown in the figure. This will require us to do work, which is stored by the system as potential energy of the spring. Now because of this potential energy, the bound state of the system is unstable. If we release the catch, the blocks will fly apart and the stored energy will reappear as kinetic energy. As shown, of the unstable bound state is greater than the sum of the separate rest masses m1 and m2 of the blocks when far apart, that is case C. Now in classical mechanics, you would have thought that m is equal to m1 plus m2. But in relativistic, this is true that capital M, which is the mass of the unstable bound state, is greater than m1 plus m2. As long as the two blocks remain together, we can treat them as a single body, whose rest mass we denote by capital M. If the body is at rest, then according to the definition of rest mass energy, we can write down the total energy in case B, when they are in bound state, is equal to capital M C square, because they are not moving. So it's only total energy is just the rest mass energy. Now if we gently release the catch, the two blocks, as I told you before, will fly apart. Once they are well separated, we can treat them as two separate objects or bodies with rest masses m1 and m2. And in that case, the total energy can be written as, and these individual total energies of individual masses can also be written as the sum of their relativistic kinetic energy and rest mass energy. And from law of conservation of total energy, we get this equation. Now since the two blocks in case C are both moving, so K1 and K2 are both greater than 0. Therefore, this mass of the bound state is actually greater than the sum of individual rest masses. And we can find out the change in mass or rest mass as capital M minus the sum of two other masses. This is our equation 2. So from equation 1 and 2, we get this relation. So here K1 plus K2 is the total kinetic energy released as bodies fly apart. We can say that the mass delta M or change in the rest mass has been converted into kinetic energy. The rate of exchange between mass and energy being given by the familiar equation energy equals to mass times c square. Kinetic energy released as the bodies move apart is the same as the work done to bring them together in the first place. Therefore, delta mc square is equal to the work done to push those bodies together, as in case B in their bound state. Now let's quickly see an example. In this reaction, thorium is converted into radium and helium. Now this thorium is actually naturally unstable. And Ra here is radium. The combined energy of the two atoms, radium and helium, is 4 mega electron volt. Question is, by how much should the rest mass of the parent differ from the combined rest mass of its offspring? We have just seen this relation between the change in mass and kinetic energy of individual two objects or bodies. This is given as 4 mega electron volt, and we can convert it into joule by multiplying it, and then we can get delta M. This mass difference in the range of 10 to the power minus 30 kg is actually very small, even compared to the masses of atom involved. Nevertheless, it is large enough to be measured directly. In another similar question, you can look at a conversion of a subatomic particle to a proton and a negatively charged pion. If the momentum and masses of this proton and negatively charged pion are given, now you know the units of mega electron volt per C or mega electron volt per C square. If the question is find the rest mass of this subatomic particle. Now in this particular case, since we know this relation that E square is equal to Pc square plus square of mc square, using this equation we can get energy of proton as 1103 mega electron volt and energy of pion as 292 mega electron volt. Now we know that the energies of these two in this reaction is conserved because law of conservation of total energy. So we have this, and we can get the energy of this subatomic particle. Similarly, using the law of conservation of momentum, we can get the momentum of this subatomic particle. Now using above equation and rearranging to get the mass, we get the mass of this subatomic particle as this. So we get this rest mass of that subatomic particle. So with this we have come to an end of our chapter, and in the next class I will start the new chapter on thermal radiations, but I will advise you to go through all the questions in the textbook and some examples also.